In this video, let's start with a basic question. If we have a function, any function, over here, and we just call it fx, and let's set a line from here, which is at x of 3, and somewhere over here, which is the x of 7, say, how do we get the area under this curve fx from 3 to 7? So the area over here. How do we get that area? Well, we can introduce a new principle of calculus called the integral. And to solve this problem, we can use an integral notation like this. From 3 to 7 fx dx. And solving for this will give us the area under this curve. In this video, we're just going to tell you how to solve, what this actually means, the definition of this. In the next video, we're going to tell you how to solve one of these. So what does this actually mean? What does all of these fancy symbols, these small letters, these big letters, what do they all every mean? So, one big area over here we can think of as being comprised as a lot of different slices. So if we just if we have a slice over here, slice over here, slice over here, and each one of these little rectangles will give us each one of these little short or tall rectangles added together will give us this approximate length area under this curve. Because when the width of the rectangle becomes so very small, the little slope that happens during the little curve becomes negligible. So basically, the area under this curve is the tiny rectangles that sprout down from it, that are sliced from it, in infinitesimally thin slices, and if we get those slices of skinny rectangles together, we can get the total area. So, about slicing these rectangles to form a big area, to slice thin rectangles to add them up to do a big area, that's essentially what we're talking about with integrals. We're slicing something small into thin slices so you can add them up to get the total thing. But back to this notation. What does this notation actually mean? We know that dx, we've seen it in dy dx. Dx means the small distance of x. When the change in x becomes so very small, it becomes so infinitesimally small, then it changes into a d. The delta changes into a d. And we can see that this 3 represents this 3, and this 7 represents this 7. Now let's break this down into its individual part. This part, which is the integral sign, this is the function, and this is the dx. And just like in derivatives, this dx can participate in calculations like a normal variable. Okay, with this notation, let's just take a random slice. So if we have a slice here, to here, over here. In reality, the thickness of this slice would be dx, which is infinitesimally thin. But I can't draw something that's infinitesimally thin. But if we have maybe infinite numbers of these strips going down and we add them up, then we will get our total area under the curve. But let's just focus on this little strip for now. So, let's name this point over here just any random point. We know that the thickness of this would be dx. The thickness of this little slice would be dx. And we know that the height of this little thin slice would be fx, if this is our x. So our area of this thin little slice would be dx times fx, which we can clearly see here. So this fx times dx gives us the tiny little area for this one little slice. And what does this mean? This basically looks like a big S, and S stands for sum. So basically, we add all of the the slices from 3 to 7, and then we'll get our total area. Basically, this says that we're gonna go from 3, we're gonna take all the slices all the way up to 7, and we're gonna add them up. We're gonna add all those areas up. And you can expect to see like from a slice here, 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 all the way through, then we'll get an area of the total curve underneath.